In this video, we'll discuss world-building metals, where they're found, how they're mined, as well as the roles that different metals play in world-building cultures and civilizations. Hey everyone, my name is Matthew, at least after I've been smelted down and purified, and this video is part of a series where I'll be going through a science-adjacent world-building process step by step. For today's video, we'll be looking at metals, discussing whereabouts on fantasy maps different metals can be found. We'll also be looking at the development of metallurgy, establishing the order of metals that sapient species are likely to mine and smelt, before looking at how the use of different metals can determine the technological progression for fantasy civilizations. So, without further ado, welcome to the World Building Corner. Alright, let's do this. When we refer to metals, we're referring to entire categories of elements on the periodic table. And although some elements are contentious in category, there are 95 elements of the 118 known elements that are considered to fall into the category of metals. Metals can either form as a native metal, meaning that it is pure and unmixed with any other elements, such as copper, or as a chemical compound, meaning that it's bonded with another element to form something new, such as copper sulfate. Assuming a planet is Earth-like, very few metals can resist natural weathering processes like oxidation over geological timescales, with only copper, silver, gold, and the platinum group, more commonly called PGE, surviving natively in large quantities. It's for this reason that for much of history, the metals in regular use were mostly limited to this list, as well as other metals commonly found in the same deposits, like nickel, tin, and lead. Iron is unique among the list of commonly used metals across history in that while it's found in reasonable abundance across Earth, native iron is practically non-existent within the surface crust, with the vast majority existing bonded to silicate, which is very costly to extract, even by modern standards. Iron oxide materials like hematite, while comparatively rarer, are the primary source of iron we deal with. And unless you have a fictional species with more advanced technology than we have currently in real life, these iron oxide compounds are what we'll be working with. In a modern world, even rare and obscure metals like osmium have a use, which for reference is the rarest metal in the Earth's crust, at about 50 parts per trillion, and is today used as an alloy for things like needles and electrical contacts. However, this short list of metals available in significant and accessible quantities for much of history are what we'll be focusing on today. Importantly, metals aren't usually just found laying around, but are instead contained within rock or sediment that can then be mined. These rocks and sediment that contain metals are called ore, and when an economically significant amount of this ore accumulates, it's considered an ore deposit. Ore deposits almost never feature a single metal, and there are trends for which metals will be included based on what caused the ore to form, a concept which is called oregenesis. Oregenesis can be caused by 4 different mechanisms: magmatism, hydrothermal movement, sedimentary accumulation, and metamorphism. By nature of their temperature and pressure requirements, metamorphic deposits found at minimal depths are exceptionally rare. So for today, we'll be focusing on the other 3 processes. This is the map of Locus, the fictional world that we've been creating across this series. Let's go through the different types of ore deposits and progressively place them on the map. For this process, we'll need to see our tectonic plates, so we'll overlay those on top. To begin with, let's start with magmatic deposits, which form as part of the melting and crystallization process of magma, wherein multiple native metals are melted down and then separate from the silicate rock as it cools. The primary two examples of this process are nickel-copper and PGE deposits, both found in stable continental interiors, away from plate boundaries. Diamond deposits also form in the same locations, but are very rare. Unfortunately, outside of rare and unique geological circumstances where deposits are closer to the surface than usual, mining of magmatic deposits is going to be limited to cultures with access to industrial machinery. However, if a volcanic hotspot forms nearby these deposits, it's possible for the minerals to be present closer to the surface, even in erupted material, making them readily accessible at or near the surface. On Locus, given that our cultures are still in the ancient era, let's grey out the copper, zinc, PGE and diamond deposits that aren't easily accessible, and leave coloured the ones around volcanic hotspots. Next up, we have our main hydrothermal deposits, which form due to the movement of hydrothermal water within the planet's crust that causes physiochemical reactions. Often, this process is caused by magmatic intrusion or tectonic upheavals. VMS deposits predominantly include copper and zinc, with secondary amounts of silver, gold, lead, tin, and other trace minerals. They can be found very simply in and around mountainous regions, both new and old. They're formed through hydrothermal activity on seafloors, which in modern oceans we refer to as black smokers. Over geological time periods, the volcanic activity that causes mountains to rise brings these deposits up to mineable locations. VMS deposits are perhaps the most important as world builders, as their association with rift environments makes them far more accessible, especially to early civilizations. An excellent real-world example are the VMS deposits found in Cyprus and the Sinai Peninsula, responsible for the overwhelming majority of copper that was mined and used in Eurasia since 5000 BC. Porphyry deposits mainly feature either copper with gold or molybdenum as secondary minerals, or tin with tungsten as a secondary mineral. All kinds of porphyry deposits also include small amounts of lead, silver, and zinc. These deposits form along mountain ranges on the overriding side of volcanically active convergent plate boundaries. That is, the mountains on the edge of the plate that's moving on top of the other. However, despite having excellent mineral yield, especially of copper, porphyry deposits are found in locations and depths that are less accessible and require more advanced mining techniques. In fact, the first mining of porphyry deposits on Earth coincided with the invention of steam shovels and railroads, meaning that for all pre-industrial cultures, these rich sources of minerals are functionally inaccessible. So let's grey them out for now on Locus. As fluids escape these porphyry deposits, however, they reach the surface as hot springs and bring with them minerals along their journey. Minerals that deposit between the original porphyry and the hot springs are called epithermal deposits, featuring gold with secondary amounts of silver and copper, and trace amounts of lead, zinc, and mercury. While all epithermal deposits tend to have gold and silver present, copper tends to be deposited relatively close to the parent porphyry deposit, while lead and zinc deposit further away, with the furthest epithermal deposits including mercury. Epithermal deposits, by definition, are closer to the surface and therefore more easily accessible than porphyry deposits. And there are instances of historical mining of epithermal deposits, such as within the Arabian-Nubian Shield, which is responsible for much of the gold mined by the Nubian Empire. Unsurprisingly, deposits closer to the surface have mines established earlier in history than those closer to their porphyry parents, which means that for Locus, our early epithermal mines will be those featuring gold, silver, and mercury, rather than lead or zinc, and almost certainly not copper. So we can grey out those that are closest to their porphyry parents. Further away from the plate boundaries again are IOCG deposits, featuring iron, copper, gold, and in much lower quantities, uranium. These form similarly to porphyry deposits, though are associated with much older and therefore smaller mountains. IOCG deposits are exceptionally high yield, with contention that they may be the densest naturally occurring concentration of any metals. However, like porphyry deposits, the technology required to mine them puts them out of reach of early civilizations. And on Earth, we've only opened mines in IOCG deposits in the 21st century. So for now, we'll grey them out on Locus. Finally, we have our sedimentary deposits, formed due to environmental factors, such as erosion or deposition. Sedimentary deposits are the most accessible and easiest to mine, so we'll be leaving all of them up on our map. The question is not whether an early culture can access sedimentary deposits, but rather whether they're useful and in what order. BIF deposits are sedimentary deposits that feature iron oxides, found in and around old mountains. Assuming a planet is Earth-like, during ancient periods with high atmospheric oxygen, less iron could be contained within ocean water, which sank and formed bands of iron oxide. Just like our earlier VMS deposits, volcanic activity over geological time periods causes these deposits to rise up to mineable locations. SEDEX deposits, mostly containing lead, zinc, and silver, can be found in continental sedimentary basins, which are areas with a land depression that were once seafloor that are now continental. Sedimentary deposits can also be created from other deposits when water is involved. Secondary enrichment deposits are made when rain dissolves an ore deposit and shifts the minerals downstream. These secondary enrichment deposits can form on effectively any of the previously mentioned deposits, though are more likely to form in areas with higher rainfall. MVT deposits follow a similar process but drag and deposit minerals down and out from underneath mountain ranges and into continental zones, putting them much further away from their source deposits. If a mountainous deposit exposes native metals which then erode into a river, the minerals can be carried by said river until they accumulate into what's called a placer deposit. Placer deposits are found along the riverbeds of rivers that flow downstream of mountainous ore deposits. In addition, heavy rainfall in rainforests, both tropical and temperate, causes soil leaching, creating residual deposits of aluminium. Finally, while not considered an ore, let's quickly place coal on our map as well, as coal will eventually be used as a source of fuel to work the metals we're discussing. Coal can be found in areas that were once tropical and subtropical swampland millions of years ago, specifically at least 250 million years ago. For Locus, we have maps from 250 million years ago, 500 million years ago, and 750 million years ago, with the quality of coal in modern times increasing the further back it formed, though it does become more complex to mine. We can place the coal deposits on these maps and then translate them into roughly the same continental locations for the modern map. Though for now, we'll grey out the oldest coal deposits, which are likely to be too deep for early mining. Importantly, coal deposits on Earth-like planets are very abundant, so don't be shy about placing a lot of it. So, now that we've placed our metals and coal on the map, let's discuss how they're used by cultures and civilizations. prehistoric cultures, especially those within the Upper Paleolithic, Mesolithic, and Neolithic, shape native metals found on the surface, such as those found in placer deposits, using a process called cold working, where metals are worked at ambient temperatures with tools like hammers. Gold, being the softest metal on our list of available metals, is unsurprisingly the first and easiest metal to be cold worked, though its softness makes it unsuitable for use in tool making, instead being used mostly as jewelry-like adornments. While some metals like gold can be cold worked, most require hot working, which is more commonly referred to as smelting, the process where metals are heated to their melting points to separate them from their impurities, making them more malleable. This is a critical development stage for cultures, and if a culture for whatever reason is unable to utilize fire, they won't be able to progress technologically past this point. The first metals likely to be properly smelted are tin and lead, due to their melting temperatures being around 230 and 330 degrees Celsius respectively, both within the temperature range of a simple campfire. However, tin and lead are historically non-impactful discoveries, as both are still too soft to use for structural elements, tools, or weapons. Instead, the metal that provides the turning point for early cultures is copper. While it is possible for copper to be cold worked to a degree, to work it properly does require smelting. However, copper has a melting point above 1,000 degrees Celsius, which is above the output expected from a campfire, instead requiring a dedicated smelting structure, such as a kiln, as well as a fuel source like coal, which we tend to expect not from a culture that's migratory, but rather from one that has settled down and is established. To begin with, the coal, gold, and copper-bearing deposits close to the major settlements of Locus are likely to have mines established, with coal used as a fuel, gold used decoratively, and copper used both decoratively and functionally. Once a culture begins smelting and making tools of copper, it's said to have transitioned out of the Stone Age and into the Copper Age. Copper, silver, and gold have similar melting temperatures, meaning they're likely to begin being smelted at the same point of technological development, which is consistent with real-life findings from the Copper Age. It is at this point historically that coins of copper, silver, and gold were first introduced, revolutionizing currency and many concepts of trade. While the use of copper in tools does bring an improvement in quality over stone, the biggest jump forward is the discovery of bronze. Bronze is not a native metal, but rather an alloy between copper and tin, and is much harder and more durable than copper, marking a significant improvement in tools, and perhaps most importantly, in weaponry. Bronze is considered such a huge jump forward that we only consider the Copper Age to be important as a stepping stone towards the Bronze Age, where most tools are made of bronze. On Locus, the settlements of Norford and Thuchus have ready access to both copper and tin, as well as to coal, making them the most likely first locations for bronze to be discovered, definitively transitioning Locus out of the Stone Age and into the Bronze Age. This sets up both the Norfordian and Thuchusian civilizations as their respective continental powerhouses of both trade and military. And while they have this advantage, their neighbours are likely to either placate them through trade or bend under their might, with some of the smaller neighbours likely to be absorbed into what will become the first empires of Locus. Before we finish up though, let's quickly discuss iron, which has a melting point of over 1,500 degrees Celsius, far higher than the other metals we've discussed. For ancient cultures, this makes iron impractical to smelt and almost impossible to work. So while BIF deposits are easily accessible right from the dawn of civilization, it will be some time before ironworking is introduced. Similarly, even though aluminium has a melting point of only 660 degrees Celsius, the aluminium found in residual deposits requires a huge amount of energy to purify. So while it is accessible, it's unlikely to be used significantly until cultures become industrial. So, to recap, metals are found either in pure native forms or as part of a compound which must be worked to purify. Orogenesis can occur magmatically, hydrothermally, or sedimentarily, with different ore deposits being more or less accessible to civilizations depending on their technology. Cultures are likely to begin using native metals like gold, but will progress to mine and smelt other metals, purifying and working them into tools. Copper marks the first step towards better tools, though bronze is the true big step forward out of the Stone Age and into the future. Join me next time when we'll discuss currency and trade, having our cultures take the next step out of the isolation of prehistory towards a more connected and diverse world. You can find all the information in this video as well as other resources for world building in general over at worldbuildingcorner.com. And if you've enjoyed this video, don't forget to like and subscribe to follow the world building journey. And until next time, stay awesome.